Hello friends, welcome back once again. This is Nagaraj SK, Lecturer of Computer Science and Engineering Department, Jain Polytechnic, Belagavi. So, in this session, I am going to continue with lecture number 50 and 51 of Unit 6 Greedy Technique. So, here I am going to explain you about Kruskal's algorithm, how exactly this Kruskal's algorithm works. So, in the previous section, we considered the greedy algorithm that grows in a minimum spanning tree through a greedy inclusion of the nearest vertex to the vertices already in the tree. And there is another greedy algorithm for the minimum spanning tree problem that also always yields an optimal solution, that is named as Kruskal's algorithm. After uh, Joseph Kruskal, who discovered this algorithm when he was a second year graduate student, and Kruskal's algorithm looks at a minimum spanning tree of a weighted connected graph as an acyclic subgraph with number of vertices minus one edges for which the sum of the edge weights is the smallest. So here Kruskal's algorithm. Kruskal's algorithm is a famous greedy algorithm and it is used for finding the minimum spanning tree, that is MST, of a given graph. To apply Kruskal's algorithm, the given graph must be weighted, connected and undirected. The tree that we are making or growing usually remains disconnected and grows a solution from the cheapest edge by adding the next cheapest edge to the existing tree or forest. And Kruskal's algorithm is faster for sparse graphs. So consequently, the algorithm constructs a minimum spanning tree as an expanding sequence of subgraphs that are always acyclic but are not necessarily connected on the intermediate stages of the algorithm. The algorithm begins by sorting the graph's edges in non-decreasing order of their weights. Then, starting with the empty subgraph, it scans this sorted list, adding the next edge on the list to the current subgraph if such an inclusion does not create a cycle and simply skipping the edge otherwise. So here we have a pseudocode of this Kruskal's algorithm, that is Kruskal is a function, it is taking an argument that is a graph G. So Kruskal's algorithm for constructing a minimum spanning tree, and what input we are passing to this algorithm is a weighted connected graph, that is G equal to phi comma E, where G indicates that it is a graph and phi stands for vertices and E stands for edges. And what output we are going to get from this is the set of edges composing a minimum spanning tree of G, and that we are storing it in the ET, and that is the set of edges composing a minimum spanning tree of graph G. And then to begin with this Kruskal's algorithm, we have to sort whatever edges are there in non-decreasing order of the edge weights, something like weight of ei1 less than or equal to dash 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 less than or equal to w weight of ei, that is edge, number of edges. So we are going to initialize some of the variables like et and e counter and k variables to 0, and et is initialized to null, that indicates initializing the set of tree edges and its size, and initialize the number of processed edges, that is k. So initially the set of minimum spanning tree is null, that is et, and while e counter less than number of vertices minus 1, that is number of vertices minus 1 do, what we are doing, k equal to k plus 1. If et if union of eik is acyclic, then et is equal to et union of eik, then e counter will get increment, that is number of selected edges will get increment, e counter equal to e counter plus 1, and we are finally going to return et, that is set of edges composing a minimum spanning tree of the given graph tree Z. Then for example, here we have an example, it is consisting of a b c d e f, total 6 vertices, and it is a connected weighted connected acyclic graph. So here we need to identify uh, the minimum spanning tree for this given graph. So how to begin with this, right? Here we have the tree edges like AB is there, BC is there, then B to F is there, A to E is there, A to F is there, C to F is there, F to C is there, F to D, and D to E or E to D. Something like this we have edges. From this given graph we need to identify first which is the smallest edge, smallest weighted edge we need to identify. So here the edge we have is this one, that is B to C, that we are selecting first. It is the weight of this edge is 1, so that is the least among all the other edges in the given graph, so that we are selecting B to C. Then after that which is the next smallest edge in the given graph, so it is E to F or F to E, that is the weight is 2, this we are selecting. Then the next edge we are going to select is, just by observing that we can come to know that A to B is 3, then that will be the next minimum edge that we are selecting to form a minimum spanning tree. Then the next smallest edge is B to F. One more is there, C to F. We can arbitrarily select if the tie occurs, because there are two edges with the same value, that is same weight 4 4, B to F and C to F. So any one we can select from this. So we are selecting B to F, this one. Then after that we are selecting the next minimum edge, that is 5. 5 is the again there is a tie, A to F is 5 and F to D is 5. If you select this A to F, this edge if you select this edge, that is if you select this one, it will form a cycle, and if you select this one also, if you select C to F, even it is 4, this will also form a cycle. So we have to carefully select that it should not form any cycle there. So that is the reason we are going to select F to D, which is having the minimum, which is having next minimum value edge, that is 5, that is F to D. Then finally just a minute, then we visited all the edges, so we visited all the vertices. So the minimum spanning tree will be something like this: A to B, B to C, then B to F, F to D, and F to E. This will be the minimum spanning tree for this the given graph. So this is how the Kruskal's algorithm we can apply for the given graph for finding the minimum spanning tree of graph G. Then analysis of Kruskal's algorithm. The edges are maintained as min heap. The next edge can be obtained in big O of log E time if graph has E edges. Reconstruction of heap takes big O of E time. So Kruskal's algorithm takes big O of E log E time, and the value of E can be at most big O of V square. So big O of log V and big O of log E are same. That is, worst case time complexity of Kruskal's algorithm is E log V or E log E, that is number of edges and number of vertices. That is about analysis of Kruskal's algorithm. Then we have the disjoint subsets and union find algorithms. So Kruskal's algorithm is one of a number of applications, and it requires a dynamic partition of some n element set S into a collection of disjoint subsets S1, S2 till Sk. Deals with an abstract data type of a collection of disjoint subsets of a finite set with the following operations. Make set X creates a one element set X. Find X returns a subset containing X. Union X comma Y constructs the union of the disjoint subsets Sx and Sy containing X and Y respectively, and finally adds it to the collection to replace Sx and Sy which are deleted from it. So the most implementations of this abstract data type use one element from each of the disjoint subsets in a collection as that subset's representative. Some implementations do not impose any specific constraints on such a representative. Others do so by requiring, say, the smallest element of each subset to be used as the subset representative. Also, it is usually assumed that set elements are integers or can be mapped into as integers. There are two principal alternatives for implementing this data structure. The first one, called the quick find, that optimizes the time efficiency of the find operation, and the second one is called the quick union, which optimizes the union operation. The quick find uses an array indexed by the elements of the underlying set S. The array's values indicate the representative of the subsets containing those elements. Each subset is implemented as a linked list whose header contains the pointers to the first and last elements of the list along with the number of elements in the list. So under this scheme, the implementation of make set of X requires assigning the corresponding element in the representative array to X and initializing the corresponding linked list to a single node with the X value, and the time efficiency of this operation is obviously in theta of 1, and hence the initialization of n singleton subsets is in theta of n. The efficiency of find X is also in theta of 1. All we need to do is to retrieve the X representative in the representative array, and executing union X comma Y takes longer. So a straightforward solution would simply append the Y's list to the end of X's list and update the information about their representative for all the elements in the Y list, and then delete the Y's list from the collection. This is how This is how this disjoint subsets and union find algorithms works. And next we have summary. So let me summarize uh, this what we discussed so far. So we understood what is Kruskal's algorithm and the pseudocode of Kruskal's algorithm, finding minimum spanning tree using Kruskal's algorithm and examples, then analysis of Kruskal's algorithm, and finally disjoint subsets and union find algorithms. So this is all about this session. If you are having any doubts in this, please do ask your queries. Thanks for watching.